About nuclear energy and how to generate nuclear energy using nuclear reactions. Okay, the first type of nuclear reactions is nuclear fission, where by using a neutron we can bombard or shoot the neutron into an atom, and that atom will split its nucleus and release other neutrons to generate another unstable nuclei, which is much smaller. Yeah. The isotopes that we use for this kind of fission is the uranium isotopes, yeah, and then usually they split to generate smaller daughter nuclei and in that process they release some radiation like gamma rays, and also they release energy as well that we can capture in forms of nuclear reactors and nuclear power plants. Yeah. So during the fission reaction, we said that the neutron is bombarded, which means it's being shot at the nucleus, and then it collides with this unstable nucleus, and then the nucleus will split into smaller nuclei, and we call this the daughter nuclei, and then this process can be repeated in a chain reaction. So for that fission reaction we need to apply some conditions. First we need to have a uranium nucleus which is unstable, and then we can shoot some neutrons or one neutron, and that neutron will then break it down to a smaller nuclei, two, namely krypton and also barium nucleus, and then they will release three other neutrons. Yeah, and then these three other neutrons can collide with other uranium nuclei and then create a fission chain reaction, which requires a critical mass to keep this chain reaction continuation where it keeps repeating this cycle. Yeah, so the critical mass for uranium is around 52 kgs of uranium nucleus, and then once you reach the critical mass it can keep generating a chain reaction. So for that we can use this concept and have nuclear power plants to use this radiation and that energy to generate basically electricity, useful energy for us, using the basic concept of the AC power station, yeah, where we use the steam generated from that powerful reaction and the high pressure as well, where we can rotate turbines, and then the turbines will then use the AC generator to convert that kinetic energy into electrical energy, or in other words we use the thermal energy from the radiation or the nuclear reaction to produce some steam, and the steam can be used in exchange of rotating this turbine to generate electricity at the end. Yeah. So at the core of this power plant we have the control rods that provide the reaction, and then this reaction would be controlled using the water pump to control its temperature, and then the steam released from the pressure valve or the pressure vessels will go through the pipes, and then the pipes will lead it to the turbine, where the turbine will move through steam, and then the motion of the turbine will then generate electricity in the AC generator. Yeah. And then we can also talk about some controls and safety measures that we have inside the nuclear reactor. So first we said we need to have some control rods. These control rods are made out of graphite core, which control the rate of this reaction at which they produce the neutrons throughout the control rods. Yeah? And then we need also a shield of some sort to protect the reactor from leakage or also seeping radiation. So we need to have lead walls or concrete walls to protect the reactor. And then this will help us ensure there is no pollution due to leakage from outside of the reactor. And also we need to perform periodic checks and maintenance to the whole power plant or the nuclear reactor and the machinery inside of it. And we need to make sure there's safe disposal of any nuclear waste that come out of this nuclear reactor. And the second type of nuclear reactions we can talk about is nuclear fusion, which occurs mainly, we know it to be happening in stars or in the solar system, in the sun in particular. So when two light nuclei join to form a heavier one, this is basically the nuclear fusion, where two light nuclei will join together to form a heavier one, and that process will usually generate high amounts of energy. Yeah? It's very demanding. It needs a lot of extreme high temperatures, and therefore it's not possible to replicate that on Earth, and it happens in the stars where they use this nuclear fusion to produce energy. In most stars it's usually a fusion of hydrogen atoms together to form helium particles. Yeah? The process of solar fusion takes place in most solar and stellar stars in the universe. So they fuse mainly hydrogen into helium, and it requires a very large sum of temperature, so 15 million degrees Celsius. That's why it's hard to replicate on Earth. And that consumption or conversion of hydrogen into helium is limited, because there is a limited amount of hydrogen in every star. So this process is non-renewable, since hydrogen is non-renewable inside the star, and it has limited time before the star will run out of hydrogen. Now, let's talk about some sort of background radiation that can be present without any nuclear reactions. We can talk about those as the existing radiations that happen all around us without any interference from us. There are two types of those radiation. They can be natural sources or man-made sources that occur due to the inventions of medicine or nuclear generation of power. So let's talk about the main ones that we know about. We need to mention the radon gas, which comes from the soil, and then the rocks and buildings material that exists all around us in urban environments, and then the medical contribution or the medicines like the X-ray machines, CT scans, and then the food that we know is also decaying and producing some radiation, and then cosmic rays coming from the sun and other radiations as well. Let's talk about the natural sources first. So as we said, radon gas that's present in air comes from the soil or the ground, and it has a natural decay cycle of the uranium in the rocks or in the soil. It has no smell, no color or flavor. However, if it stays in our lungs, it can cause a lung cancer due to the alpha particles bombarding with our cells in our body. And then we can talk about the rocks and the buildings, where they also have this kind of decay of the uranium and radium particles. Another form we need to mention from the natural sources is the cosmic ray from space coming from the sun. So the sun emits a number of protons every second, and some of them can reach us into our atmosphere, and then they can collide with the air particles in the atmosphere, which can produce some gamma radiation as well. And lastly, we can talk about the carbon-14, which is existing in all biological matters that inhale the carbon-14 into their organic matter, and then that amount is usually constant because they exhale and inhale a regular supply of carbon in their system. However, when matter they die and they start decaying, we can use that carbon to date their age by knowing what is the leftover amount inside their matter. So lastly, we need to talk about the man-made sources. So the man-made sources mainly talk about the medical sources like the X-ray machines, the CT scans, and also radioactive trackers that can be consumed to track some radiation inside the body, or radiation therapy. And others that are very obvious, which is the nuclear waste due to the nuclear power plants, nuclear reactors, which they don't contribute directly to background radiation, but if there are some seepage or dangerous handling from the people using those nuclear waste, or maintaining and protecting us from the nuclear waste, they can also get some radiation from them. And then the nuclear fallout that happened due to the nuclear weapons, where the nuclear weapon can create nuclear explosions, and those explosions will definitely give out some background radiation up to a certain number of years. And then lastly, we can talk about some nuclear accidents that happen in some exposed area that were exposed to high nuclear radiations in the past, an environment like Chernobyl, which also emits some radiation over time up to a certain extent. And these accidents are not so common, but they can ruin the place for a number of decades.